Chapter 8 discusses exponent rules. One thing that you need to be aware of going into this chapter is that this chapter requires a lot of memorization. So the slides in our PowerPoint are not going to be extremely long, but if you do not remember the rules, then you're going to have a hard time with this chapter. So make sure you take good notes, and if you have questions about the individual rules, make sure that you watch the slides more than one time to get additional help. Also, you'll need to print out your PowerPoints before starting the VoiceThread lessons. That way you're prepared to take your notes. Once you've done that, you're ready to begin. We're going to start the chapter by giving you a few definitions. Our first definition is a monomial. A monomial is one term. It's a number or a variable or a combination of number and variables. Just to review on our example here, your coefficient is the number that's multiplying the variable. Coefficient is also a base. A base is any number an exponent can hang on to, meaning any number that might have an exponent raised to it. And then our exponent is the number that tells the base to multiply itself that number of times. Our first exponent rule that we come to is adding numbers with exponents. This is something that we've been doing all along this semester, so it's nothing new. We're just actually giving you a reason for why we've been doing the things we've done in algebra thus far. Basically, when you have an addition problem, all you're doing is combining like terms for terms that have the same variable and the same exponent. So many of you have seen your teachers draw shapes to show you to combine like terms. 3x squared plus 4x squared equals 7x squared. You just add your coefficients and you keep your variable and exponent the same, and that's supposed to be squared. Okay, for our second example, we are only combining like terms if they have the same variable and exponent. So what else in the problem has an x to the third? Well, you've got 6x to the third, and then we have a negative 3x to the third. But then we also have two other terms in the problem. You've got negative 2xy to the third plus 8xy to the third. So it's very important that we keep our terms together. When we combine our like terms, 6x to the third minus 3x to the third gives us 3x to the third. When we combine our negative 2xy to the third plus 8xy to the third, we're going to get 6xy to the third. And we need to separate these terms with the plus sign because our 3x to the third was positive. Now some of you might be wondering why I put my 6xy to the third at the beginning instead of after 3x to the third. The reason that we do that will be discussed in chapter 9, so don't worry about that right now. Okay. All right, in our third example, we need to think about what combines with 9x. We also have a 3x, and nothing else combines with that. Then our x squareds need to go together. And now that we've identified everything that we're combining, we're ready to write out our problem. So, negative 5x squared plus 2x gives us negative 3x x squared, and 9x plus 3x give us plus 12x. So that's just a quick review on adding like terms. All right, so for our practice example slide, again, we're just combining like terms. So my x squared combines with negative 3x squared, and I have a 5x, and I also have a negative 6xy. So all three of those are their own terms and they need to be combined accordingly. So we need to write this as x squared minus 3x squared would be negative 2x squared. And then our next term, based on the number of exponents that we have, should be minus 6xy plus 5x. Our next example, we're combining like terms again, so I have 17x, and the only other x in here that's alone is the negative 2x, so they'll combine together. My 3y combines with 8y, and then I also have my negative 5xy. So we bring down negative 5xy. Then we're going to go in alphabetical order. So we're saying 17x minus 2x, which gives us a positive 15x. And then 3y plus 8y, which gives us a positive 11y. And our final example, again, we're combining like terms, so 4x to the fifth combines with 2x to the fifth. Negative 6x to the third does not combine with anything, nor does 5x squared. So when we write this out, 4x to the fifth plus 2x to the fifth gives us 6x to the fifth. Then our next highest exponent is the negative 6x cubed. And then our last term would be plus 5x squared. And that's our review on adding numbers that have exponents. It's just simply combining like terms and adding your coefficients. Okay, so the exponent rule when you have 0 as an exponent should be any number raised to the 0 power equals 1. Okay? It's a pretty simple definition when you think about it. When you have 5 to the 0 power, because it's raised to the power of 0, that whole term equals 1. If you look at the second example, you have negative 2 to the 0 power. That whole term equals 1. Our third example, however, is a little different. There's only one portion of the problem that's raised to the 0 power, which is 3 to the 0 power. So essentially what you're doing is you're saying 19x to the 8th raised, or times 1, which is simply 19x to the 8th power. The only thing that changes to 1 is the base that is raised to the 0 power. All right, so we're going to do a few practice problems with 0 as an exponent. In our first example, notice that the 0 is attached to the base, which is really parentheses. In this problem, you have a negative outside of the parentheses. So the problem is -1 times 23 to the 0 power. The only thing being raised to the 0 power is the 23, because the 23 is inside of your parentheses. Therefore, you have -1 times 1, which is simply -1. In the second example, you have 3ab to the 0 power. The only base raised to the 0 power is your b. That cancels out to a 1, leaving you with 3a times 1, which is simply 3a. The third example, you have the quantity 2x cubed y to the 4th all to the 0 power. Because this 0 is attached to the parenthesis, everything inside of the parenthesis turns into a 1. So that whole term just equals 1. Our next example, 5 to the 0 power x squared. 5 is the only number with the power of 0, so that cancels out to 1 times x squared, which is simply x squared. And then our final example, we have two different bases raised to the 0 power. So 9 to the 0 power is 1 times y to the 7th, and then x to the 0 power is also 1. So our final answer would simply be y to the 7th power.
Now we're going to talk about multiplying numbers that have exponents. As was said earlier in the lesson, an exponent tells its base to multiply itself that number of times. So what does it mean when I ask you to expand 4 to the 3rd power? Well, it means that 4 is multiplying itself 3 times. So again, it means 4 times 4 times 4. So let's expand these other problems as well. X to the 4th, where x is the base and it's being taken to the 4th power, simply means x times x times x times x. X to the 4th power. 3x to the 2nd power here, you need to be careful with. The base of x is the only base that has the 2nd power. So 3 has a power of 1 on it. So this, when we expand it, is 3 times x times x. Again, only the base of x has the power of 2 on it, so that's the only thing that gets expanded there. Now, this next example is actually 2x inside of parentheses all to the 5th power. This does mean that 2 and x are going to multiply itself 5 times. So if we ask you to expand an exponent, it simply means to multiply itself that number of times. So over here, we're going to simplify some expressions. Simplify means to consolidate all variables into one place if at all possible. This problem is read x to the fourth times x to the third. If we think about expanding this, x to the fourth means x times x times x times x. And this x to the fourth is times x to the third, which simply means it's going to be times x times x times x again. So here's the x to the fourth right here, and here's the x to the third. And notice all those x's are multiplying each other. Now expanding is not simplifying. Expanding shows how we would simplify. If I were to give you x's multiplying themselves 7 times, I hope that you would be able to tell me that this would equal x to the 7th power. Do you notice a shortcut? X to the 6th times x to the 7th. So again, if I want to expand this, this is going to be x times x times x times x times x times x, so 6 times. And then x to the 7th is x times x times x times x times x times x times x. And when you get finished, if you count up how many x's are multiplying themselves here, you will come up with x to the 13th power. Again, this is a multiplication problem, but I hope by now you have noticed on a multiplication problem that deals with exponents, instead of actually multiplying the 4 and the 3 on this first example, hopefully you see that the shortcut would be to add the powers. Again, on this second example right here, x to the 6th times x to the 7th, is there a shortcut that works the same way it did on this first example? 6 plus 7 is 13. So on this final example, x to the 42nd times x to the 52nd, I hope that you would see the shortcut would be the way to go here, because I don't want to write x to the 42nd expanded or x to the 56th expanded. So I'm going to learn here that this could be done by saying x to the 42 plus 56. And 42 plus 56 gives us x to the 98th power. So now we're going to talk about the actual law of multiplying numbers with exponents, or multiplying bases with exponents. The law is simple. When multiplying numbers with exponents, you simply add the powers on like or similar bases. So, again, you're going to add the powers on like or similar bases. So, on this first example here, x to the 5th times x squared, if we expanded it, we would have x times x times x times x times x times x times x, which would give us x to the 5 plus 2 is 7. So that would be x to the 7th power. This second example, this one is tricky for students. When I have 3 to the 4th, if I expanded it, it would be 3 times 3 times 3 times 3. And that 3 to the 4th is multiplying 3 squared, which would be 3 times 3. So if I had all of those 3's multiplying each other, this answer would be 3 to the 6th power. Do not be tempted to actually multiply the base of 3 and the base of 3 together. The base, as noted below here, the base stays the same when you're adding their exponents. Over here, this next little problem here, 4 to the second times 4 to the third, since the bases are different, you cannot use the law of exponents on adding the bases. You cannot say that 2 plus 2 up here is 4 because the bases do not match. The only thing that you could do is figure out that 4 squared equals 16 and multiply that 16 times the answer to 3 squared, which is 9. What is 16 times 9? I believe it's 144. Again, if the bases are not the same, you cannot add the powers on those bases. Which brings us to this final example, this fourth example down here. So this previous one was the third example. We have x to the third y times 2x to the fourth y times 3x y to the third. The coefficient of all these, the coefficient of the first term here is 1, second coefficient is 2, and the final coefficient is 3. 1 times 2 times 3 is 6. Notice, those are not exponents, so we still multiply those numbers. However, on the x's, each one has its own power. We have an x to the third, an x to the fourth, and an x. If I add all those powers together, 3 plus 4 plus 1, I get x to the 8th power. My next base of y, this has a power of 1 plus 3 gives me a power of 5. So that answer is 6, x to the 8th, y to the 5th. Here's an opportunity for you to practice some problems. I would recommend that you pause the PowerPoint at this time, practice these problems on your own, and then check to see if you got them right along with us. So hopefully you've practiced these, and now we're going to check to see if you did this right. 2 to the 6th times 2 to the 5th. Since the bases are the same, we can simply add the powers. So this would give you 2 to the 11th power. If you want to actually figure out what 2 to the 11th power is, you may do that. But for this case, I'm just going to leave it there because it's a rather large number. A to the third here on the second example, all right, 1 and 2. I'll go ahead and number these, 3 and 4. This next example, a to the third times a to the 10th, again, since they have the same base, we can add the powers. So this would be a to the 13th power. Excuse me. Example 3, n to the third t times n t to the 6th. Just pay attention here. The t is the only variable right here that has the 6 attached to it. The n has a power of 1. So when I go to do these, I have to add the powers on the bases that are alike, the n and the n. I have n to the third times n, so this would equal n to the fourth. Okay, pen's acting a little funny, so I'll come down here. N to the fourth. And then t, here's 1 plus 6, which would make 7. So the answer to that third problem should be n to the fourth power, t to the 7th power. Your final example, k squared times k to the 12th would equal k, 2 plus 12 is 14. So that's k to the 14th power.
All right, the next exponent law that we're going to be discussing is called the power to a power rule of exponents. A power to a power means that you are raising something inside of a parenthesis to another power. Therefore, we're going to use a little helpful hint, and we're calling it side by side you multiply. Okay, so now let's show you what this really means. What we're doing is we're taking the exponent of 2 that is attached to the parenthesis, and we are distributing it to every single exponent inside the parenthesis. Because these two numbers, 4 and 2, are side by side, we multiply them together. So when we do this, we keep our base of x, and 4 times 2 gives us 8. Okay, on our second example, we have 2x squared all cubed. Now, it's important to remember that 2 is also a base with an exponent of 1. So we're going to go ahead and write that 1 there. We distribute the 3 on the outside of the parenthesis to every exponent on the inside of the parenthesis, which gives us 2 to the third power, and then x to the sixth power. 3 times 2 is 6. Well, we have to actually simplify this math here. So when we say 2 to the third power, we have to actually find out what that number is. 2 to the third power gives us 8. And then we keep our x to the sixth power because we cannot simplify that any farther. Let's go ahead and do a few more examples on practicing the power to power rule. Again, it's a good habit anytime you do not see an exponent listed just to draw an exponent of 1 so you don't forget to distribute the power on the outside to the power on the inside. So 2 times 1 gives us 7 squared, and then 2 times 1 gives us x squared. Well, 7 squared is 49, and then x squared doesn't simplify any farther, so that's what we're left with. Our next example, you have 3n all to the fourth power. We need to actually do the distributing there, so we get 3 to the fourth power, and then n to the fourth power. Again, we distributed that. And then when we do the math, 3 to the fourth power gives us 81, and then n to the fourth will not simplify any farther, so we keep it as is. Our next example, again, put that power of 1 with the 12 so you don't forget to distribute the 3. So you would have 12 cubed, and then you have h, and side by side you multiply, so we have h to the 15th. When you do 12 to the third power, you get 1,720 h to the 15th. And our final example, we have 8 squared p to the 12th. 2 times 6 gave us 12. 8 squared is 64 p to the 12th. Product of powers is simply combining two rules that we've already discussed. It is combining the multiplying numbers rule. So when you multiply numbers, you add the exponents. And it's also combining your power to power rule. If you look at the example below, I've kind of broken it down for you. The first thing that you're always going to do is your power to power rule first. Okay, so in the first set of parentheses, we didn't have a power on the outside. But our second parentheses did have a power that we had to distribute to everything on the inside. Once we distributed that, we would have gotten x to the 6th, y to the 8th. From this point on, we're implementing our multiplying numbers rule. When you multiply numbers, you add the exponents on like bases. 2 comes down, and then we combine our 1x plus x to the 6th, which gave us x to the 7th, and then y squared plus y8 gave us y10. That's how we got our final answer of 2x to the 7th, y to the 10th. And we're going to practice a few more examples on our next slide. Let's take a look at our first example. We've got 3x squared all squared times x cubed y all cubed. So first thing that we must do is our power to power rule. So again, we have to distribute this 3 on the outside of the parentheses to everything on the inside of the parentheses. So we have 3 squared x to the 4th and we have to do it on the second set of parentheses as well, giving us x to the 9th, y cubed. So that's our first step, was to do power to power. From there we need to simplify. So we have 3 squared, which is 9. From here we just have a straight multiplication problem. When we multiply numbers, the rule says that we add the exponents on like bases. So for our base of x, we would add 4 plus 9, giving us x to the 13th. And then y cubed just comes down because it has nothing else to combine with. So let's take a look at our second example. Again, the first thing that we're always doing is distributing the exponent on the outside of the parentheses to all of the exponents on the inside. So this gives us 5 cubed y cubed. And our second set of parentheses, when we distribute to everything on the inside. So you get 6 squared x to the 6th, y squared. So here is a time that we're going to have to do a little bit more simplifying. 5 cubed gives us 125 y cubed. 6 squared gives us 36 x to the 6th y squared. Because this is still a multiplication problem, we must multiply our coefficients. So we would say 125 times 36, which gives us 4,500. Then we need to combine our like bases. So there's nothing that combines with the x. So we're just going to bring that down, x to the 6th. And we're writing that down first because x comes before y in the alphabet, and we have to write our variables in alphabetical order. And then we combine the y cubed and y squared. When we multiply numbers, we add their exponents, giving us y to the 5th. And that's our simplified answer. Our third example is pretty easy after the first two. So distribute our 5, giving us x to the 10th. And then distribute our 2, giving us x to the 6th. 10 plus 6 gives us x to the 16th power. And in our final example, first thing we want to do is distribute our 5 to all of our exponents on the inside of the parentheses. So we have 2 to the 5th power, a to the 15th power, b to the 20th. In our first set of parentheses. The second set of parentheses, we've got to distribute our 2 on the outside of the parentheses to all the exponents on the inside, giving us 3 squared, a to the 4th, b to the 6th. Simplify this farther, and you would say a to the 5th gives you 32. A to the 15th. B to the 20th. Three squared is 9. A to the 4th. B to the 6th. 32 times 9, because we have to do our coefficients, multiplying those together, gives us 288. The first variable we need to write down is our a, because it's the first letter in the alphabet. When we multiply numbers, we're adding their exponents. 15 plus 4 gives us a to the 19th. And then 20 plus 6 gives us b to the 26th.
Now we are going to look at the law of negative exponents. Our law for negative exponents is move it, which means you will move the base from either the denominator or the numerator, to lose it, which means you're going to lose the negative sign on the exponent when you move it. So when we have a negative exponent in the numerator, and the numerator is the top number, would be like 3 to the negative third. We have to remember that the denominator of any whole number is always 1. So we move the 3 to the negative third down to the denominator. When we move it, we lose the negative sign on the 3 exponent. So we have 1 over 3 to the third. When we simplify that, that gives us 1 over 27. Now let's look at having a negative exponent in the denominator. Our problem is 2 over 3 to the negative 2. 2 has an exponent of 1 that we don't write, but it's understood that it's there. Because it has a positive exponent, 2 does not move. But our denominator, 3 to the negative 2 power, has a negative exponent. So we need to move it. So we are going to move it up to the numerator. So now we have 2 times 3 to the second power all over 1. Now we can multiply. 2 times 3 to the second power is 9. So 2 times 9 will give us 18. Now let's practice with some negative exponents. Here we see that we have x to the negative 4 power. Remember, any whole number or any variable is over 1. So x to the negative 4th is like a numerator. Now, when we have a negative exponent, what we want to draw as a fraction bar, we are going to move x to the negative 4th down below and make it a positive 4. Now we need to have a placeholder up here as our numerator, so we put 1. So our final answer is 1 over x to the 4th power. Next, we have 1 over x to the negative 2 power. Because I see a negative exponent, I'm going to draw my fraction bar. 1 does not need to move, but x to the negative 2 power does. So because it's in the denominator, we move it up to the numerator and lose the negative sign. We can get rid of the 1 also because we do not need to write a 1 in front of a variable. So our final answer is just x to the second power. The bottom one that we have is x to the negative 2 over y to the negative 3. Because I see negative exponents, I'm going to draw a fraction bar. My x to the negative 2 needs to move down below to the denominator and lose the negative sign to make it a positive 2 exponent. Now my y needs to move up to the numerator and lose the negative sign on the 3 to make it y to the third over x to the second. Now let's look at 2x to the negative 3. We need to think of 2 as being separate from x to the negative 3. The negative 3 exponent is on x. 2 has an exponent of 1. So, because I see a negative exponent, I'm going to draw a fraction bar. 2 does not need to move because its exponent of 1 is positive. But x to the negative 3 needs to move down to the denominator and lose the negative sign to make it just x to the third. So now our final answer is 2 over x to the third. The next problem we have is 3x to the negative 2 power over 5y to the 0th power. 3 has an exponent of 1, so we do not have to move 3 because the exponent is positive. 5 also has an exponent of 1, so we do not need to move 5 because the exponent is positive. X to the negative 2 needs to move below because it is a negative exponent, and it changes to a positive 2 exponent. Y to the 0th power would stay where it's at, and anything to the 0th power is 1, and 1 times 5 over and x to the second power is just 5x to the second power. So our final answer is 3 over 5x to the second power. Because I see negative exponents in this last problem, I drew my fraction bar. We have negative 6x to the 4th, a to the negative 3rd, over 2y to the 3rd, b to the negative 2 power. We can simplify negative 6 over 2 because remember, anything that's as a fraction is a division problem. So negative 6 divided by 2 is going to give us our negative 3. X to the 4th is going to stay on top because it is not getting moved. A to the 3rd, negative 3rd, will move to the bottom because it is a negative 3 and we can change it to a positive 3. Y to the 3rd is going to stay on the bottom because the 3 is positive, so it does not need to move. And b to the negative 2 power would move to the numerator because it is negative and it would become a positive. So our final answer would be negative 3, x to the 4th, b to the 2nd, over a to the 3rd, y to the Now we are going to look at what we do when we have quotients of powers. Quotient means to divide. When we multiplied powers, we added their exponents. So now, when we divide powers, our rule is that you subtract exponents of the like bases, or the same bases. So, we have x to the 10th over x to the 4th. We subtract their exponents and do nothing to the base, which would mean 10 minus 4, which would give us 6. So our final answer is x to the 6th. Now let's look at the second one. We have x to the 4th, y to the 7th over x and y to the 3rd. Whenever we just have a variable or a number without an exponent, we have to remember that the exponent is 1. So we would have x to the 4th over x to the 1st. When we subtract those, we get x to the 3rd. Next, we have y to the 7th over y to the 3rd, and when we subtract 7 and 3, we get y to the 4th. So we no longer need our fraction bar, so we can just write our answer as x to the 3rd, y to the 4th, and we are finished. Now let's practice the quotient of the powers. We look at the first problem that has x to the 6th, y to the 2nd over x to the 3rd, y to the 8th. So we are going to subtract the exponents of like bases. So we have x to the 6th divided by x to the 3rd, which will give us x to the 3rd when we subtract 6 minus 3. Then we have y to the 2nd over y to the 8th. When we subtract those, 2 minus 8 gives us a negative 6. Now, we have to remember that we can't leave a negative exponent in our final answer. So we are going to have to draw a fraction bar. X to the 3rd stays on top, but y to the 6th will move below the fraction bar and lose the negative symbol. And our final answer is x to the 3rd over y to the 6th. Now, the next one we have is x to the negative 3rd, y to the 4th over x to the 2nd, y to the negative 3rd power. So again, we are going to subtract the exponents of our like bases. So our first base is x. We're going to do negative 3 minus 2. When you do negative 3 minus 2, you get a negative 5 as our exponent. Our second base is y, so we would do 4 minus negative 3. 4 minus a negative 3 will give us 7. Now we cannot leave the negative 5 exponent, so we need to draw our fraction bar. X to the negative 5 will move below to become the denominator, and we will lose the negative, so it will be x to the 5th. And y to the 7th will stay on top because it does not need to move because it is not a negative exponent. So our final answer is y to the 7th, x to the 5th, over x. Now we have y to the 4th over y to the 9th. When we subtract the like bases, we are going to do 4 minus 9, which is going to give us negative 5. So we can have y to the negative 5th power. We cannot leave our answer that way, so we're going to draw a fraction bar. We will move y to the negative 5th power below to become the denominator and lose the negative on the exponent. And on top, we need a placeholder, so we are going to put 1. And that's our final answer. 1 over y to the 5th power. The final problem we have is 15x to the 4th, y to the 6th, over 3x to the 7th, y to the 2nd. We have to remember that when we see numbers or integers in our division problems, we can divide those. So we have 15 over 3. 15 over 3, or 15 divided by 3, will give us a 5. Then we have our like bases. We have x, which is x to the 4th and x to the 7th. When we subtract 4 minus 7, we get a negative 3. Then we have y, which is 6, y to the 6th, and y to the 2nd. So we subtract 6 minus 2, and we get y to the 4th. Again, we cannot leave our problem with a negative exponent, so I'm going to draw another fraction bar. 5 is going to stay above our fraction bar because it has an exponent of positive 1. X to the negative third needs to move below, lose the negative, and keep a 3 exponent, so move it to lose it. And y to the fourth is staying on top because it does not have a negative exponent. So our final answer is 5y to the fourth over x to the third.
Okay, now we will talk about scientific notation. A number is expressed in scientific notation when it's in the form of a number times 10 to the power, where a is between 1 and 9, which is your power, and n is an integer. When you are making a very large number smaller, the exponent is positive. When you're making a very small number bigger, the exponent is negative. And so as you can see on the chart at the bottom, when you make the exponent, when you're moving the decimal to the left, it is positive, and when you're moving the decimal to the right, it is negative. Express 0.000000902 in scientific notation. First thing we want to know is where would the decimal go to make the number be between 1 and 9. Well, your decimal point is always going to go after the first non-zero number, which in this case is 9. So we would write 9 decimal point 02 because you have to write the numbers after you put the decimal point. Any numbers that are not 0, you need to make sure you put after the decimal point. Now, this is kind of an exception because there is a 0, however, it's between the two numbers, so you need to write it as well. The decimal was moved how many places? How many places was it moved from your original problem? Well, if we count 1, 2, 3, 4, 5, 6, 7, 8, it was moved 8 places. So it was moved 8. And remember, when the original number is less than 1, which this is because you've got a decimal point right there, so that is less than 1, the exponent is negative. So our final answer would be 9.02 times 10 to the negative 8th power. Okay, we're going to practice, so let's start with this one. All right, so we need to put the decimal point after the 2, and we need to include all numbers that are non-zero numbers except for this 0 because it's between two non-zero numbers. So we need to include that, and then we put times 10, and how many did we move? We moved 1, 2, 3, 4, 5, and we moved to the left, so it was positive. In the second one down here, we are going to put it after the 1, 2, 9, 2, 8, 0, 9, 4, 5, 2, 4, times 10, and let's see how many places we went. 1, 2, 3, 4, 5, 6, 7, 8, and I went to the left, so it is positive. Okay, third example goes after the first non-zero number. So after the 3, I need to include that 0 because it's between two numbers. I'm going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spots. I went to the right, so it is a negative exponent. Last example, 8.09. Keep the 0 because it's between two non-zero numbers. And then I went 1, 2, 3, 4, 5, 6, 7. I went to the right, so it is negative.
Okay, so we are going to express the following in decimal notation. 4.58 times 10 to the 6th power. Notice the exponent is positive, which means we're going to have a bigger number. Since if we move this decimal place to the right to make this number larger, we're going to move it 2 times just by moving it to the 8. But it needs to be 6 places. Therefore, I need to add more zeros, and I'm going to add 4 zeros to this number so that it would be 4 decimal places. So our number is 4, 5, 8. That's moving it 2 places. By adding 4 more zeros, to make it the 6 places that's shown here on the exponent 6. So my number, we fill in our commas, would be 4,580,000. The next one, we notice we have a negative exponent, which means we're going to add zeros to the front of this number without the decimal. So if I write my 2, 3, and 5, I see that my decimal was right here, and if I move it 1, 2, 3, and I put it right here and fill in with zeros, my number would then be 0.00235. For this example, again, we have a negative exponent, which means we are going to have a very small number. We are moving our decimal to the left 2 places. So I write my 6, 4, 2, and 1. The decimal was here originally, and if I'm going to move it to the left 2 places, the new place is right there, and I fill in a 0 for the placeholder. And I can rewrite my number as 0.06421. And for the final example, we see our exponent is a positive 5, which means our decimal place is going to move to the right 5 places. I can start with my original number, 3, 5, 3. My decimal was here. If I move it 5 places to the right, it would be 1, 2, 3, 4, 5 would be the new place. We would fill in these places with zeros, and then we don't need to write the decimal at the end. Our number is 3 zeros. And once I put the commas in, I can read this number as 353,000. So a thing to remember is with a negative exponent, you're going to move your decimal place to the left that many spaces. With a positive exponent, you're going to move your decimal place to the right that many places. Okay, we're going to use a calculator to evaluate these numbers. Using the scientific calculator or the TSI-83 calculator, When you put this in your calculator, you want to be sure to use parentheses. So by using parentheses around the whole numerator here, 4.5 times 10 to the negative fifth, you would hit the divide symbol, and you would divide it by, again using parentheses, 1.6 times 10 to the negative 2. When you put that in your calculator, using the parentheses, you get an answer that looks like this. 0.0028125. Now, if you did not get that when you put it in the calculator, try it again, but this time be sure that you put parentheses around your numerator, then hit divide, then put parentheses and your denominator, 1.6 times 10 to the negative 2. Close your parentheses. When you get this answer, you may be asked to put the answer into scientific notation form. We see that this is not in scientific notation. We need to move the decimal place to make this a number between 1 and 9.9. I see I need to move it 1, 2, 3 places. I would rewrite my answer as 2.8. I need to put the 125 with it. These are numbers over more than 0. I'm going to put times 10. Oops. And I moved my decimal place 3 times. Therefore, and since I moved it to the left, it's a negative 3 exponent. So again, when I used my calculator to evaluate this this fraction, I got my answer as 0.0028125. And then when I change this to scientific notation, I need to make it a number between 1 and 9.9 by moving the decimal place to the right 3 places. Let's try the next example. 7.2 times 10 to the negative 9, if you put this in parentheses, and you divide it by 1.2 times 10 to the second power. You get an answer in your calculator that may look like this. 6 e negative 11. Now that's the way our calculators will show scientific notation. However, you cannot write that on a test. The correct way, or the correct answer to look for on a test would look like this. 6 times 10 to the negative 11th power. And this is your final answer. This is what your answer looks like in scientific notation. Go ahead and box this answer in as well. Okay, for this example, we're going to put this into the calculator just as we see it with the parentheses. So parentheses 0.0042, close your parenthesis, open up another parenthesis, and put 330,000. You get an answer in your calculator that looks like this: 1,386. That is the answer. However, you may be asked to put it into scientific notation. In that case, we know that the understood decimal point is right here. We're going to have to move this decimal point 3 places in order to get a number between 1 and 9.9, which is important if you're going to write in scientific notation. So, I can rewrite this as 1.386 times 10. Since I moved my decimal to the left, I have a positive exponent, and I moved it 3 places. My final answer is this. And for the last example, again, you're going to put this into your calculator the way that you see it with parentheses. So you have 3600, 000, 000, close your parentheses, and then open up another parentheses, put 23, close your parentheses. The answer you get, as you can imagine, would be a lot of zeros. Let's see, we have 8, 2, 8. And we're going to have the same amount of zeros. We had 8 zeros. Okay, so this would be our answer. We're going to now put this big number into scientific notation, and since our understood decimal in a number would be right there, we need to move this decimal place all the way to between the first 8 and 2 to make this a number between 1 and 9.9. So in order to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places is what we're moving the decimal in order to write this in scientific notation. Our final answer would be 8.28 times 10 to the 10th power. Positive exponent because we moved our decimal to the left. Okay, we need to write these numbers in proper scientific notation. In this example, we notice that our number is not a number between 1 and 9.9. So we need to place the decimal in the correct spot. If we move the decimal place to the left 2 spots, our number would be 2.346. We're going to put the times 10 with it. And since we added 2 more spots to the left, then we need to add 2 to the original 9 that we had here, which would give us a new exponent of 11. So the correct way to write this 2.34 or 234.6 times 10 to the 9th in scientific notation would be 2.346 times 10 to the 11th. our number before the times 10 is a number between 1 and 9.9. And for the second example, if we put this into our calculator, 22 times 10 to the third power, you can put that in parentheses, multiplying it or opening up another parentheses and putting 51 times 10 to the negative 7. If you have a calculator, the answer that you would get is 0.1122. Then to change this to a number in scientific notation, we need to move the decimal place once to the right so that we can have a number between 1 and 9.9. 1.122 times 10. And since we moved it one spot to the right, we have a negative 1 for our exponent.